on that topic, we have to ask you about the paradox, the information paradox of black holes. What is it?
So this is what catapulted Hawking's fame. When he was a young researcher, he was thinking about black holes and wanted to just add a little smidge of quantum mechanics, just a little smidge, wasn't going for full-blown quantum gravity, but kind of just asking, well, what if I allowed this nothing, this vacuum, this empty space around the event horizon? The star's gone, there's nothing there. What if I allowed it to possess sort of ordinary quantum properties, just a little tiny bit, nothing dramatic. Don't go crazy. And one of the properties of the vacuum that is intriguing is this idea that you can never say the vacuum's actually completely empty. We talked about Heisenberg, but the Heisenberg uncertainty principle really kicked off a lot of quantum mechanical thinking. It says that you can never exactly know a particle's position simultaneously with its motion, with its momentum. You can know one or the other pretty precisely, but not both precisely. And the uncertainty isn't a lack of ability that we'll technologically overcome. It's foundational. So that there's, in some sense, when it's in a precise location, it is fundamentally no longer in a precise motion. And that uncertainty principle means I can't precisely say a particle is exactly here, but it also means I can't say it's not. Okay. And so it led to this idea that what do I mean by a vacuum? Because I can't 100% precisely know. In fact, there's not really meaningful to say that there's zero particles here. And so what you can say, however, is you can say, well, maybe particles kind of froth around in this seething quantum sea of the vacuum. Maybe two particles come into existence and they're entangled in such a way that they cancel out each other's properties. So they have the properties of the vacuum. They don't destroy the kind of properties of the vacuum because they cancel out each other's spin, maybe each other's charge, maybe things like that. But they kind of froth around. They come, they go, they come, they go. And that's what we really think is the best that empty space can do in a quantum mechanical universe. Now, if you add an event horizon, which, as we said, is really fundamentally what a black hole is, that's the most important feature of a black hole. The event horizon, if the particles are created slightly on either side of that event horizon, now you have a real problem. Okay. Now the pair has been separated by this event horizon. Now they can both fall in, that's okay. But if one falls in and the other doesn't, it's stuck. It can't go back into the vacuum because now it has a charge or it has a spin or it has something that is no longer the property of that vacuum it came from. It needs its pair to disappear. Now it's stuck. It exists. It's like you've made it real. So in a sense, the black hole steals one of these virtual particles and forces the other to live. And if it'll escape, radiate out to infinity, and look like, to an observer far away, that the black hole has actually radiated a particle. Now, the particle did not emanate from inside. It came from the vacuum. It stole it from empty space, from the nothingness that is the black hole. Now, the reason why this is very tricky is because in the process, because of this separation on either side of the event horizon, the particle it absorbs, it has to do with the switching of space and time that we talked about, but the particle it absorbs, well, from the outside, you might say, oh, it had negative momentum, it was falling in. From the inside, you say, well, this is actually motion and time. This is energy. It has negative energy. And as it absorbs negative energy, its mass goes down. The black hole gets a little lighter. And as it continues to do this, the black hole really begins to evaporate. It does more than just radiate. It evaporates away. And it's intriguing because Hawking said, look, this is going to look thermal, meaning featureless. It's going to have no information in it. It's going to be the most informationless possibility you could possibly come up with when you're radiating particles. It's just going to look like a thermal distribution of particles, like a hot body. And the temperature is going to only tell you about the mass, which you could tell from outside the black hole anyway. You know the mass of the black hole from the outside. So it's not telling you anything about the black hole. It's got no information about the black hole. Now you have a real problem. And when he first said it, a lot of people describe that not everyone understood how really naughty he was being. He did. But some people who love quantum mechanics were really annoyed. Okay, people like Lenny Susskind, Gerard 't Hooft, Nobel Prize winner, they were mad because it suggested something was fundamentally wrong with quantum mechanics, if it was right. And the reason why it says there's something fundamentally wrong with quantum mechanics is because quantum mechanics does not allow this. It does not allow quantum information to simply evaporate away and poof out of the universe and cease to exist. It's a violation of something called unitarity, but really the idea is it's the loss of quantum information that's intolerable. Quantum mechanics was built to preserve information. It's one of the sacred principles, as sacred as conservation of energy. In this example, more sacred, because you can violate conservation of energy with Heisenberg's uncertainty principle a little tiny bit. But so sacred that it created what became coined as the black hole wars, where people were saying, look, general relativity is wrong. Something's wrong with our thinking about the event horizon, or quantum mechanics isn't what we think it is, but the two are not getting along anymore. And just to tell you how dramatic it is, so the temperature goes down with the mass of the black hole, heavier a black hole, the cooler it is. So we don't see black holes evaporate. They're way too big. But as they get smaller and smaller, they get hotter and hotter. So as the black hole nears the end of this cycle of evaporating away, it takes a very long time, much longer than the age of the universe. It will be as though the curtain, the event horizon's yanked up. Like it'll literally explode away, just boom. And the event horizon, in principle, would be yanked up. Everything's gone. All that information that went into the black hole, all that sacred quantum stuff, gone. Poof. Okay, because it's not in the radiation, because the radiation has no information. And so it was an incredibly productive debate because in it are the signs of what will make gravity and quantum mechanics play nice together, some quantum theory of gravity. Whatever these clues are, and they're hard to assemble, if you want a quantum gravity theory, it has to correctly predict the temperature of a black hole, the entropy of a black hole. It has to have all of these correct features. The black hole is the place on which we can test quantum gravity.
But it still has not been resolved.
It has not been fully resolved.
I looked up all the different ideas for the resolution. So there's the information loss, which is what you referred to.
Right.
It's perhaps the simplest, yes, most radical resolution, is that information is truly lost. This would mean quantum mechanics, as we currently understand it, specifically unitarity, is incomplete or incorrect under these extreme gravitational conditions.
I'm unhappy with that. I would not be happy with information loss. I love that it's telling us that there's this crisis, because I do think it's giving us the clues. And we have to take them seriously.
For you, the gut is like
unitarity is going to be preserved.
So quantum mechanics is
we have to
holding
come to the
strong.
rescue. It's Lenny Susskind in his book Black Hole War says his subtitle is "My Battle with Stephen Hawking to Make the World Safe for Quantum Mechanics."
Quantum mechanics, I love it.
It's something to that effect.
So then, from string theory, one of the resolutions is called fuzzballs. I love physicists so much. Originating from string theory, this proposal suggests that black holes aren't singularities surrounded by empty space and an event horizon. Instead, they are horizonless, complex, tangled objects, aka fuzzballs, made of strings and brains roughly the size of the would-be event horizon.
Yeah.
There's no single point of infinite density and no true horizon to cross.
In some sense, it says there's no interior to the black hole. Nothing ever crosses. So I gave you this very nice story that there's no drama. Sometimes that's how it's described at the event horizon, and you fall through and there's nothing there. This other idea says, well, hold on a second. If it's really strings, as I get close to this magnifying quality and the slowing time down near the event horizon, it is as though I put a magnifying glass on things, and now the strings aren't so microscopic. They kind of smear around, and then they get caught like a tangle around the event horizon, and they just actually never fall through. I don't think that either, but it was interesting.
So it's just adding a very large number of extra complex
degrees of freedom.
Yeah.
There are no teeny tiny marbles to fall through.
But it's similar to what we already have with quantum mechanics. It's just giving a
But
deeper,
it's
more
really
complicated.
saying the interior's just not there ever. Nothing falls in. So the information gets out because it never went in the first place.
Oh, interesting. So there is a strong statement there.
There's a strong statement there, yeah.
Okay, so soft hair challenges the classical no hair theorem by suggesting that black holes do possess subtle quantum, quote, hair. This isn't classical hair-like charge, but very low energy quantum excitations, soft gravitons or photons at the event horizon that can store information about what fell in.
Worth trying, but I also don't think that that's the case. So the no hair theorems are formal proofs that the black hole is this featureless, perfect fundamental particle that we talked about, that all you can ever tell about the black hole is its electrical charge, its mass, and its spin, and that it cannot possess other features. It has no hair is one way of describing it. And that those are proven mathematical proofs in the context of general relativity. So the idea is, well, therefore I can know nothing about what goes into the black hole, so the information is lost. But if they could have hair, I could say that's my black hole because it have features that I could distinguish, and it could encode the information that went in this way. And the event horizon isn't so serious. It isn't such a stark demarcation between events inside and outside, and where I can't know what happened inside or outside. And I don't think that's the resolution either, but it was worth a try.
Okay, the pros and cons of that one. The pros, it works within the framework of quantum field theory in curved spacetime, potentially requiring less radical modifications than fuzzballs or information loss. Recent work by Hawking, Perry, Strominger revitalized this idea. The cons is that the precise mechanism by which information is encoded and transferred to the radiation is still debated and technically challenging to work out fully, and indeed, it needs to store a vast amount of information. Okay, another one. This is a weird one, boy. Is ER equals EPR.
This is probably it, though.
Oh, boy. So ER equals EPR is Einstein-Rosen bridge equals Einstein-Podolsky-Rosen bridge posits a deep connection between quantum entanglement and space-time geometry, specifically Einstein-Rosen bridge, commonly known as wormholes. It suggests that entangled particles are connected by a non-traversable wormhole, so tiny wormholes connected. Okay.
I can say that this is not a situation where we can follow the chalk. We can't start at the beginning and calculate to the end. So it's still a conjecture. I think it's very profound, though. I kind of imagine Juan Maldacena, who's part of this, with Lenny Susskind. They were kind of like, oh, it's like ER equals EPR. They couldn't even formulate it properly. It was like an intuition that they had kind of landed on and now are trying to formalize. But to take a step back, one way of thinking about ER equals EPR, you have to talk about holography first. And holography, both Juan Maldacena really formalized it, Lenny Susskind suggested it. The idea of a black hole hologram is that all of the information in the black hole, whatever it is, whatever, entropy as a measure of information, whatever the entropy of the black hole is, which is telling you how much information is hidden in there, how much information you don't have direct access to, in some sense, is completely encoded in the area of the black hole. Meaning, as the area grows, the entropy grows. It does not grow as the volume. This actually turns out to be really, really important. If I tried to pack a lot of information into a volume, more information than I could pack, let's say, on the surface of a black hole, I would simply make a black hole. And I would find out, oh, I can't have more information than I can fit on the surface. So Lenny coined this a hologram. People who take it very seriously say, well, again, maybe the interior of the black hole just doesn't exist. It's a holographic projection of this two-dimensional surface. In fact, maybe I should take it all the way and say, so are we. The whole universe is a holographic projection of a lower dimensional surface, right? And so people have struggled, nobody's really landed it, to find a universe version of it. Oh, maybe there's a boundary to the universe where all the information is encoded, and this entire three-dimensional reality that's so compelling and so convincing is actually just a holographic projection. Juan Maldacena did something absolutely brilliant. It's the most highly cited paper in the history of physics. It was published in the late 90s. It has a very opaque title that would not lead you to believe it's as revelatory as it is. But he was able to show that a universe like in a box with gravity in it, it's not the same universe we observe, doesn't matter. It's just a hypothetical called an anti de Sitter space. It's a universe in a box. It has gravity, it has black holes, it has everything gravity can do in it. on its boundary is a theory with no gravity, a universe that can be described with no gravity at all, so no black holes and no information loss problem. And they're equivalent. That the interior universe in a box is a holographic projection of this quantum mechanics on the boundary, pure quantum mechanics, purely unitary, no loss of information. None of this stuff could possibly be true. There can't be loss of information if this dictionary really works, if the interior is a hologram, a projection of the boundary. I know that's a lot.
Yeah. So there's some mathematics there, there's physics, and then there's trying to conceal what that actually means practically for us.
Well, what it would mean for us is that information can't be lost, even if we don't know how to show it in the description in which there are black holes. It means it can't possibly be lost because it's equivalent to this description with no gravity in it at all, no event horizons, no black holes, just quantum mechanics. So it really strongly suggested that quantum mechanics was going to win in this battle, but it didn't show exactly how it was going to win. So then comes ER equals EPR, a visual way to imagine what this means. So ER has to do with little wormholes. EPR, Einstein, Podolsky, Rosen, has to do with quantum entanglement. The idea was, well, maybe the stuff that's interior to the black hole is quantum entangled, like EPR, quantum entangled, with the Hawking radiation outside the black hole that's escaping. And that quantum entanglement is what allows you to extract the information, because it's not actually physically moving from the interior to the exterior. It's just subtle quantum entanglement. And in fact, I can kind of think of the entire black hole. If I look at it, and it looks like a solid shadow cast on the sky, some region of space-time. If I look at it very closely, I will see, oh no, it's actually sewn from these quantum wormholes, like embroidered. And so when I get up close, it's almost as though the event horizon isn't the fundamental feature on the space-time. The fundamental feature is the quantum entanglement embroidering the event horizon.
The embroidering is just tiny wormholes. So the quantum entanglement is when two particles are connected at arbitrary distances.
And they're connected by a wormhole.
And in this case, they would be connected by a wormhole.
So the reason why that's helpful, it helps you connect the interior to the exterior without trying to pass through the event horizon.
The cons of this theory is highly conceptual and abstract. The exact mechanism for information retrieval via these non-traversable wormholes is not fully understood. Primarily explored in theoretical toy models. Whoa, Gemini going hard. Theoretical toy models like the anti-de Sitter space-time, rather than realistic black holes.
True. We do what we can do in baby steps.
So another idea to resolve the information paradox is firewalls. Proposed by Ameri, Marov, Polchinski, and Sully, AMPS. This is a more drastic scenario arising from analyzing the entanglement requirements of Hawking radiation to preserve unitarity and avoid information loss. They argued that the entanglement structure requires the event horizon not to be smooth, not to be the smooth, unremarkable place predicted by general relativity, the equivalence principle. Instead, it must be a highly energetic region, a, quote, firewall that incinerates anything attempting to cross it. Okay, so yeah, that's a nice solution. Just destroy everything that crosses this. Do you find this at all a convincing resolution to the information
I would
paradox?
say the firewall papers were fascinating and were very provocative and very important in making progress. I don't even think the authors of those papers thought firewalls were real. I think they were saying, look, we've been brushing too much under the rug. And if you look at the evaporation process, it's even worse than what you thought previously. It's so bad that I can't get away with some of these prior solutions that I thought I could get away with. There was a kind of duality idea or a complementarity idea that, oh, well, maybe one person thinks they fell in, one person thinks they never fell in, and that's okay. No big deal. They sort of exposed flaws in these kind of approaches, and it actually reinvigorated the campaign to find a solution. So it stopped it from stalling. I don't think anyone really believes that at the event horizon, you'll find a firewall. But it did lead to things like the entangled wormholes embroidering a black hole, which was born out of an attempt to address the concerns that AMPS raised. So it did lead to progress.
So for you, the resolution would...
I'm going back to the vacuum,
you go back
the
to
empty
vacuum.
space, the beautiful event horizon.
Yep.
I'll give up locality, meaning that I will allow things to be connected non-locally by a wormhole.
So that is the weirdest thing you're willing to allow for, which is arbitrary distance connection of particles through a wormhole. But quantum mechanics must be preserved.
I'll entertain pretty weird things, but I think that's the one that sounds promising. The implications are so dramatic because this is why you start to hear things like, wait a minute, if the event horizon only exists when it's sewn out of these quantum threads, does that mean that gravity is fundamentally quantum mechanics? Not that gravity and quantum mechanics get along and I have a quantum gravity theory and I now know how to quantize gravity. Actually, something much more dramatic. Gravity is just kind of emerging from this quantum description, that gravity isn't fundamental. And what is the only thing that we have when we go rock bottom, when we go deeper and deeper, smaller and smaller, is quantum mechanics. So all of this, like space-time looks nice and smooth and continuous, but if I look at the quantum realm, I'll see everything sewn together out of quantum threads. And that space-time is not a smooth continuum all the way down. Now, people already thought that, but they thought it kind of came in chunks of space-time. Instead, maybe it's just quantum mechanics all the way down.
Quantum threads, so these entangled particles connected by wormholes.
Yeah.
So that's how would you even visualize a black hole in that way? So it's all, it's all sort of from our perspective in terms of detecting things, the light going in, it's all still the same. But when you zoom in a lot,
to the quantum mechanical scale at which you're seeing the Hawking radiation, you would be noticing that there's some entanglement between the radiation that I could not explain before and the interior of the black hole. So it's now no longer a perfectly thermal spectrum with no features that only depends on the mass. It actually has a way to have an imprint of the information interior to the black hole in the particles that escape. And so now, in principle, I could sit there for a very long time. It might take longer than the age of the universe and collect all the Hawking radiation and see that it actually had details in it that are going to explain to me what was interior to the black hole. So the information is no longer lost.
So information is not being destroyed. So in theory, you should be able to get information.
Now, I can't do that any more than I can recover the words on that piece of paper once it's been burnt. But that's a practical limitation, not a fundamental one. It's just too hard. But when I burn a piece of paper, technically the information is all there somewhere. It's in the smoke, it's in the currents, it's in the molecules, it's in the ink molecules. But in principle, if I took the age of the universe, I should be able to, in principle, reconstruct the piece of paper and all the words on it.